Hello and welcome to my channel. Today, we're going to dive into one of the most fascinating and mind-bending concepts in quantum physics, the wave-particle duality. In the classical world, we're used to thinking of things as either particles or waves. Particles are localized objects like baseballs or marbles, while waves are spread-out disturbances that propagate through a medium like water waves or sound waves. However, in the quantum realm, things behave in a way that defies our classical intuition. Particles can exhibit both particle-like and wave-like behavior depending on the circumstances. This is known as the wave-particle duality. Wave-like behavior of particles. Let's start with the wave-like behavior of particles. One of the most famous experiments that demonstrate this is the double-slit experiment. In this experiment, a beam of particles, such as electrons, is fired at a barrier with two narrow slits cut into it. If electrons were purely particles, we would expect them to pass through one slit or the other and create two distinct bright spots on the screen behind the barrier. However, what we actually observe is an interference pattern, which is a characteristic of waves. This interference pattern arises because each electron passes through both slits simultaneously, behaving like a wave that can interfere with itself. The resulting pattern on the screen shows alternating bright and dark fringes, just like you would see with waves of water passing through two openings, particle-like behavior of waves. Now let's look at the particle-like behavior of waves. In certain situations, waves can transfer energy in discrete packets or quanta, as if they were made up of particles. This phenomenon was first observed in the photoelectric effect, where shining light, a wave, on certain metals causes the ejection of electrons, particles. The key observation here is that the energy of the ejected electrons depends only on the frequency of the light, not its intensity. This implies that light must be quantized, with each quantum or particle of light, called a photon, carrying a specific amount of energy determined by its frequency. This particle-like behavior of light is also evident in the Compton effect, where X-rays, waves, scatter off electrons, particles, and transfer discrete amounts of energy and momentum, just like colliding billiard balls. Wave-particle duality in action. So how can something be both a particle and a wave at the same time? The answer lies in the idea of complementarity proposed by Niels Bohr. According to Bohr, particles and waves are not mutually exclusive concepts, but rather complementary descriptions of the same underlying reality. In some experiments or situations, the particle nature is more apparent, while in others, the wave nature is more prominent. The specific behavior we observe depends on the experimental setup and the type of measurement we perform. For example, in the double-slit experiment, if we try to determine which slit each electron passes through, the interference pattern disappears and we see only two bright spots, as if the electrons were behaving like particles. This is because the act of measurement or observation itself disturbs the system and causes the wave-like behavior to collapse into a particle-like state.